Alright, so this is to quickly add our variables. We have k and d, we have z, we have p, and then if we want to look at interference, we can do that as well. K is the capacity, that's the storage parameter, however many items can be held. N is the set size. D I'll talk about in the next slide, but that's the probability that the items are held in memory or uncoded, and that's proportional to capacity and set size. Z is the lapse parameter, and this isn't used probably as much as it should be, but Z is the probability that the item was attended to. And the idea is that you test for Z when capacity is greater than the set size, so that could be 1, that could be 2, and the mistakes that are made are attributable to this Z, and then you factor that into the calculation for capacity. The problem with not accounting for Z is that if you don't look at lapse parameter, you end up underestimating the capacity of the participant, because about 5% of the time it's been shown the participant doesn't encode the display, not because their capacity is less than n, but because they just weren't paying attention. The last variable we're looking at, well, depending on if we want R, is precision, and we'll just call that P. And I think that the value of looking at precision, there's been a couple interesting studies where they show that precision can actually be a more sensitive index than capacity. So you can detect more subtle changes in working memory. You can see how much this idea of resolution or precision has changed within a year. And so this one study by Hayes found that even the resolution of where set size was 1, the resolution or precision of that item changed within a year. And they had controlled for sensory motor and fine motor precision with that task. Alright, so one of the main ideas is that if D, which is the probability that all of these 4 items will be uncoded, D is the probability that these items will be uncoded, and that is equal to capacity over set size. So if a participant's capacity is 3 and this current set size, as we have here, is 4, then the probability that they will answer correctly, that all these items will be uncoded, is 75%. Because if that participant uncodes these 3 items, but this is the one that's tested, then the participant will answer incorrectly. And if you do enough trials with enough arrays that change and enough that stay the same, you can detect the capacity. But if the participant had to click on each of these items that changed, not only would you get a better idea of the guessing behavior of that participant, but you would also more accurately be able to say how many items did this participant hold in capacity. Because if all the items changed and they weren't able to identify all of those changes over enough trials, you would be able to say that the participant doesn't have a capacity of 4. So the trials you get from each array would be whatever your set size is, because each of these items is now being tested, whether they stay the same or whether they change. That all factors into the signal detection equation of hits minus false alarms. So we now have the number of items within an array times the number of trials we have. So in a trial where each of the items changes, this would rotate, and if we're on precision level 0, all items rotate at least 45 degrees. So let's say this rotates down, this rotates up, this could rotate up, it could even rotate further, and this could rotate up. Now all these items have changed, and the participant would have to identify that each of these items changed. And then I'll go over, so the number of items that change versus stay the same depends on the hits to false alarms rate that you want for the signal detection equation. But I do think that it's best that we keep the number of trials that change high, and so it would be no less than let's say no less than 2. So in a set size of 4, we would have at least 2 items that change, and hopefully keep it high to 3 and 4. The higher the amount of trials that change, the better reading I believe we get on capacity. Because if all these items change and the participant isn't able to identify all of those changes, we can conclude with the D equals K over N that their capacity is lower because they weren't able to hold each of these items in memory and detect a change. This idea, the proportion of hits to false alarms that's ideal, I think that is something that could be solved mathematically by someone who knows a lot more about that than me. But again, I think the more that we keep our change trials high, and each of these items is a change, or each of these items is a trial, but the more that we keep each of those high, the better reading we get on someone's true capacity, which allows us to very quickly locate someone's capacity. Because rather than having one array be a trial, we now have however many trials we have of each condition, as well as our multiplied by whatever the set size of n. So in this, again, we just have 4 individual trials. Before talking about how we get a participant to their capacity and controls we have, as well as what do we do with a participant once they're at their capacity, let's just look at what one trial looks like with a set size of 4. This is precision level 0, so all items will not rotate less than 45 degrees. However, any one of these items can change, and ideally we'll have it such that more than 2 will change. Alright, so here we go. Alright, which changed? Alright, so then you have to go ahead and click on each individual item that changed. Don't worry about the ones that didn't, since those won't factor into the adjustment production task. So we click on this one, this one, this one. And this part could either be timed such that after they finish clicking quickly, all of these turn into production tasks, or, and this might just be easier to program for, we have a blue button right here that they press so that we know that they're done. Alright, so that button will look like this. We go ahead and click this once we've changed our items, and then a plus minus appear for each of those changed items. Obviously, if it stays the same, they won't be changing anything. What they have to do now is rotate it back to the original orientation. So I would have to go here and press and hold that down until this rotated back to its original orientation. I would have to go ahead and hold down minus until this rotated to its original position, and then I would hold down the plus here, and that would go up until that rotated to its original position. There's other ways that this could be done. So we could have a plus equal to it'll rotate every 5 degrees or 10 degrees. But I think in general, if we want precision, the best thing to do is just that they have to hold it down, and then they can do, fine tuning with either tapping the plus or minus. And then when they are all good, they go ahead and they click another button. And so, for instance, this could just move to the top, and then they click it again once they're finished adjusting all of these. This production task is especially important because it informs guessing behavior. We get a better idea of when the participant guesses, when they haven't held all of the set size items into their memory, and it gives us a better idea of when they're guessing in those instances. It gives us more control because we can now toss trials with an angular deviation, so how much they change it back to the original orientation. If that's over, let's say 30 degrees, whatever, we can toss that individual trial. And remember that the individual trials are each individual item. So let's say that this was supposed to be rotated up there, and they rotated it here, or they rotated it here. We can just completely toss that trial. And then production tasks are a measurement of itself. So, right, how well a participant can detect or reproduce that change tells us a lot about their degree of precision, which can relate to which relates to resolution, possibly in this idea of conjunctive features, which Luck and Vogel showed in their 1997 experiment. And again, this idea of production precision that was done in this Hayes study. They could detect changes in working memory with regard to precision in only one item. So yeah, so I do think production is production precision is an important part of or there's valuable data that come out of that. And the other thing is that the production task, as we have it here, where it's not single probe, because there have been single probe production precision tasks, like the Hayes study, but the whole display, if it were to be more taxing, because after they click on all these items, then they go back, right, and this one would maybe be easier than by the time they got to this one, though we would also have some idea of why would they click here first and then here and then here. Is it because this is where they remembered, this is where they best remember the target, and then this is second, this is third, and there'd be no effective recency because it's not a single probe, it's a whole probe, so we'd have an idea of where their attention was. But this idea of consolidation, let's say it is harder, right, by the time they get to the third item versus the first. Well, would those, I see I misspelled this here, would some students who are able to get all of these correct at a very high precision level, would they have superior possibly consolidation? And if we're looking at the longitudinal ACE study with Ed Neuro, would these students have some kind of capacity that would allow them to do very well in math or on specific reading tests? And then just in terms of back-end data we'd collect, so we would first collect the response time to go ahead and click on the items that have changed, and then we could get the response time for each production task. So actually, quickly, just in thinking about it, maybe if we wanted to get the response time of each individual production task, what we could do is, after they rotate this down, they go ahead and they click on it. They rotate this to where its original position, they go ahead and they click on it. They do that here. They go ahead and they click on it. And then there's the ITI, and they go to the next trial. And then the one other thing, so we do have levels of precision. So we have the 2 or 3 levels, depending. But so this is still level 1 because these items haven't rotated more than 45 degrees, but technically the precision we get on the production task allows us to get precision scores for even when we're not, at precision level 1 or 2. The last important thing that this, I think that this design for a visual working memory change detection task allows us to get at really is this idea of distributive resources versus item distribution models. So if we really see, right, now we're really holding the participant accountable for the items that they can remember and getting a better sense of what they really can remember. We can see as set size goes up, so from 3 to 4 to 5, is this idea of precision, their ability to detect precision, is that ability really decreasing? And if it's not, and their capacity is 4, and after 4, their precision dramatically decreases, well, that would support item, that would support, this item limit model. Whereas if they're still at 7 items, they can't remember all of, every single change that happened, but they can remember some information about, about every item or most items, then that would actually be supporting the distributive resources model. The problem with a sole production task, where it just comes up as this, is that we would have to come up with some equation that says, within this amount, within these degrees, you're correct, and if it's outside of that, you're not. And this specific design allows them to tap. So we can identify, okay, they were correct, and we can estimate capacity. We can also estimate precision, because these, as the levels, as precision levels go up, there's a finer rotation, and we can assess that because they have to click. But then we also get a more liberated assessment by them having to actually reproduce that. And both of those tasks, right, the actual identification and then the production, I think will both help to inform the distributive resources versus item limit models. All right, so now let's move on to controls. If you look at this part of scalpel, you see we have set size equal to 1. We're testing for precision or resolution. At set size 1, sensory motor, lapse parameter, to talk about here. I say 15 control trials. We need a solid control through which to test precision or interference if we want to look at interference as well. The other interesting thing to look at with lapse parameter would be how that might correlate with a high variability score on the SAT or a low sustained score. I think there's interesting things that we can find with one item, like can we replicate the Hayes study in terms of finding an ability to increase precision within one school year. It's also a control for motor precision, and it's also control for our Z, for our lapse parameter. So the number of false alarms that happen when set size is 1 is accountable or attributable to a lapse that the participant wasn't attending to the array of 1 set size, 1 item. All right, so did it change? It did, so we go ahead and we click on it, and then if we want to go with the green circle down here, we go ahead and click on the green circle. We're good to go. We've gotten the RT from when we adjusted it here to when that green circle was clicked on. And then we now have the two dials here, and we have to rotate it so it goes back down. Okay, so we want to get it so it's back here. Actually, the other thing I forgot to mention is that we don't, I believe, want the bars ever to be on, so the sample array, the first array, I don't think we ever want them to be horizontal or perhaps even vertical, because I think that just is an easier way to chunk the information. And so, you know, if the participant remembers that it was like this, it's very easy to bring it, you know, back down to a horizontal level, you know, to remember that information. You know, it's much harder, I think, to detect it at, you know, to bring the rotation to 45 degrees. And so I think that's one way we control against chunking, or that we're not actually really testing capacity all the time. All right, so and then yeah, so after we click on the item, these show up, and at the same time, this is brought up here, and then after they're done rotating, they can go ahead and click on this again, and we know they're done, and we collect the RT from that. All right, so how many control trials do we have? I think we've got to think about this. I think because we're trying to get at three different things, right? How well can they be using this? How long does it take for them to do the production task? We're also getting at the lapse parameter, right? So when the precision level is at 0, how many how many trials are they getting right? How many trials are they missing? So we're calculating the Z parameter, and then the last thing we're calculating, which I think is also worthwhile, is that idea of the Hayes experiment, that you know, within 1 year you could gain the ability to be more precise in your working memory. The other thing that can be done ultimately, right, because precision we think of as kind of resolution, and, you know, similar to this idea of conjunctive features, but, you know, ultimately down the road we could actually do conjunctive features. So, you know, each item has, you know, also has a red circle on it, and, you know, this has a red square, and the way in which we look at each individual item, or that you know, that the participants held accountable for identifying the changes in each individual item, I think could possibly bring new light to that conjunctive features experiment. That, you know, really when the participant does need to identify the changes and recreate those changes, we might find out that they didn't actually hold in their working memory the complete resolution of each of you know, of the set size. Alright, so the degree of this change, and then right click on it, obviously it changed, and not all of them, right, have to change or should change. I click on it, I have this green box here which I click on, and then these come up. I have to rotate that to its original position, right, which was back here, and this is precision level 1. So the degree change is going to be 22.5, half of 45. We could even start the change at 45 degrees, but I think there's a couple studies looking at precision. The most interesting ones talk about the finer degrees of precision, and that maybe this is just falls under regular change rotation. So then we might do 5 trials at precision level 1, and then 5 trials at precision level 2. and precision level 2 would be 11.25 degrees. And then we could even go to 5.625. There was a study by Salmela and Saarinen that looked at 6-degree intervals, and they claim that there's a steady increase in standard deviation as the number of items increased to 6, and they claim that perhaps their findings differed from a couple others which showed a plateauing as capacity limit is exceeded, which is the item limit model. They claim that possibly because of the other studies' low sampling of data. So they did 6-degree intervals. So if we wanted to go lower, we could do that. Samhala and Saarinen, I think their sample was also 8 people, 2 of which were themselves. So I think when they're criticizing low sampling of data, they had a pretty low sample size. So I guess it kind of depends how many trials we want. But if we want to keep it, as short as possible, probably best to just look at 2 levels and then the 0 level, which is rotating no less than 45 degrees. So at item 1, with just one item, set size 1 item, we'd be looking at, depending on our control, 25 of this. Arguably, we might not need as many controls or as many trials because they're also doing the production task. But again, I think the answer to that is more mathematical in terms of the conclusions we want to make than it is my own intuition. So, and I could reach out. It seems like there's a group of very thoughtful people that are very into the math behind calculating visual working memory, and so maybe reaching out to one of them once we figure out like the entirety of what we want the design and everything to look like. So then we go up to 2 trials, and because we don't want these to be, I think it would just be much easier when they're doing the production task to rotate them back to vertical or horizontal. Let's start them at at 45 degrees. Okay, and then we have the change task. I click on these. Let me go ahead and click on this. So I have to bring this down, I have to bring this up. And I do that by going ahead and clicking on the plus here and the minus here to bring that up there. And then I'm done, so I go ahead and I click on both of those. And so we just got 2 trials from that. And then the next one, there'll only be 1 change. Alright, so here's our next trial. Only 1 item changed. I click that, I click here. Then we get this, and I would need to press plus to go ahead and rotate it back down to get it to its original orientation. So again, if I clicked this one, but I brought it this way, we could create some kind of algorithm that would just toss out this as being marked correct when I tapped on it. Because obviously if I didn't, I couldn't even reproduce even part of it, or brought it to the wrong side, it probably shouldn't be counted correct. And so we get a much better, a much clearer, less noisy results to then calculate capacity using signal detection and hits and false alarms. So I think with 2 we might want to do something like 20 trials, and so we'd go 10 where 1 or 2 items would change, but they're at precision level 0, which is that they the change is always greater than 45 degrees or equal to. This will continue to give us a better idea of the lapse parameter. We might even start getting into the measurement of capacity, especially if we're talking about 3rd graders or below. And then from there, if we detect that there's students that are at their capacity, we can then move forward with testing them at precision. We also continued to get some idea of the relationship between precision and capacity, or precision as a function of capacity, and and that will ultimately inform whether working memory looks more like something of an item limit or resource distribution, right? If a participant has very high capacity or very high precision when their capacity is low, and as capacity increases relative to set size, so we have something that looks like this, where this is K over N. This is capacity over set size, which is also equal to D. And we have precision down here. And then so we're looking at capacity relative to N. So D is ultimately decreasing because K is going to be constant because capacity is fixed. So N is the thing that is making D, that is making the probability that items are encoded. That's what's making D decrease. But then also you have this added variable precision. And so as precision increases, what's the nature of this slope? And then if N remains constant, we set N, we look at N in individual conditions where set size is 3, 4, whatever. How does that affect precision, and how does this slope change? All right. I'm just going to speed it up here. This is taking a while. So we start participants after N equals 1 or 2 at N for the mean age group. So for instance, for 8th graders, N would be equal to 3. So we'd start all 8th graders at N equals 3. The thing that is nice about having our adaptivity set to set size is that it's relatively natural, since K is fixed and N increases, so we have this proportion of D is equal to K over N. We can then look at precision relative to D. So D is going to be the same for everyone, it's just dependent on what the capacity is relative to the set size. And so we can look when someone's fully loaded with visual working memory, how are they performing with precision. And that's also why we should stress this idea of the control at capacity. So not only with one item, but getting a good enough trial count when when we find them at capacity, and then we start loading with precision, and then possibly interference. All right, so how does this work? Well, we give them 10 trials. No, scratch that. We give them 12 trials. If they answer 12 trials with 95% accuracy, so that lapse parameter is built into that, they would move on to set size 4. If they answer with 80 to 95%, they stay at set size 3. They have 10 more trials. And then if the total amount of trials is 95% or above, if they can bring that number up, or actually maybe that seems very hard to do. So let's discuss that. But if they bring the number up enough, then they can move up to set size 4. If not, they would remain at set size 3, and we'd begin testing on precision. And the student would rest before we start doing that. Okay, if the student answers below 80%, we'd assume that the capacity is just too high, and we'd go ahead and move them down to 2. And then again, since we've already tested them at 2, we could just start them right at precision. They'd take a rest, and yeah. And what's also nice is that these percentages or proportions will also correspond to D. So where K is high relative to N, the students under the high threshold assumption, these students should be scoring near correct, right? And the high threshold assumption is that if the items are, distinguishable and there's this discrete slots model, there's discrete slots available, then, and if K is greater than N, then again they should be getting them entirely correct besides that lapse parameter. And then ideally there'd be an algorithm that could just toss out the trials that were obviously guessed, because when they went to reproduce to the original orientation, it was so far off that we'd assume that they were wrong, and so that we could then put that into this equation of 80%, and if they're below, they would go to an easier set size. All right, and then if we move over, so again, the students that were greater than 95%, I keep messing this up, students that were greater than 95% would move to n equals 4. 12 trials, 95%, they go ahead and move to n equals 5. They stay at 4, same deal. 10 more trials. If they can raise their proportion, then they would go higher. If not, they would stay there. And this should actually be n equals 5, and this should be n equals 4. Alright, so what does the participant do when they've reached their capacity? Okay, first thing, they take a break, inform the participant that there's a chance that the rotation of the target might decrease. So yeah, I do think we have to tell the participant that they should be aware of trying to detect the subtlety of precision. All right. Participant moves to precision level 1, which is 22.5 degrees, complete 7 trials. And it doesn't necessarily have to be at 22.5 degrees and 11.25. We could split them so it would be 15 degrees, 30 degrees, and then level 0 would be 14.5 degrees. The other thing that works out quite well is that we can increase the number of trials, so the sample and change arrays, for the participants whose capacity is lower. So if we think about it like this, remember that our total trials is the trials of that condition times, or arrays in the condition times n. So if we have a set size of 4, right, and we have this, and this, and the participant is clicking on each of those, well, they're going to have a total of 4 trials within that. which is many more than someone who has a capacity of 2. And what works out well is that this participant will probably take longer to complete it, and so we can just give this other participant more trials, and we can get more information, and we'll end up actually with this same amount of total trials, because this is, again, only 2, this is 4. So then once the participant completes those 7 trials, they move on to precision level 2. They're going to go ahead and complete, we changed it to 7, but I think all of this is still open to being changed, the total number of trials. And then they go ahead and complete 11.25 degrees. And then if we do have time, I do think what will be really interesting is to see what happens with precision at k+1. So, 1 above their capacity and 1 below their capacity, and what's the relationship of precision to these conditions. And just to make it clear, the participant, so in these precision trials, these subtle precision trials, the participant continues to produce those change trials, right? So that means using, when we had the plus minus, continuing to use that to bring the target item back to its original orientation. And then this also depends on time and whether we want to test interference, but I'll continue looking at possible research of testing even more subtle rotation or precision. But if time's limited, we probably have enough. And I would look at testing these conditions, the k+1, k-1, before testing even greater precision.